Welcome, curious minds, to another deep dive. Have you ever paused to admire the intricate spirals of a sunflower?
Or maybe seen a picture of a Penrose tiling.
Exactly. Those amazing non-repeating patterns that somehow still look perfectly ordered. There's something, inherently beautiful about these designs.
People often call them sacred geometries. You find them everywhere, ancient art, the natural world.
But here's the really mind-bending part.
Hmm.
What if these very same mathematical blueprints, these ancient patterns, hold the key to designing the next generation of electronics? Maybe even computing.
It sounds like science fiction, doesn't it?
It really does. Today, we're taking a deep dive into the fascinating world where these elegant patterns meet tiny magnetic ripples, known as spin waves.
That's right. And maybe just a quick definition for anyone new to the idea.
Good idea.
So think of spin waves as collective oscillations, like ripples, but in a magnetically ordered material.
Okay, like ripples in a magnetic pond.
Sort of, yeah. Ripples of magnetic orientation traveling through a material. In quantum terms, we talk about their basic units, their excitations, as magnons.
Magnons, got it.
And they carry energy and information, much like light waves or sound waves do, but they're fundamentally magnetic.
So our mission for you on this deep dive is to explore how researchers are, well, deliberately engineering magnetic materials with these intricate patterns.
And not just because they look cool.
Right.
Yeah.
Not just for beauty, but to precisely control these spin waves. It's a journey that starts with, abstract math.
And moves pretty quickly into cutting-edge applications that could genuinely redefine how we process information.
Okay, let's unpack this a bit. We're talking about periodic patterns.
Mm-hmm.
So designs that don't just repeat in a simple, predictable way like a checkerboard.
Right, but they still possess a deep underlying order.
Exactly. How did scientists first realize that these specific kinds of patterns, like a Fibonacci sequence or a Penrose tiling, could actually influence fundamental physics? Especially something as subtle as, well, spin dynamics.
Yeah, that's a great question. The story really begins back in the late 1980s. It was shortly after the discovery of quasicrystals.
Ah, quasicrystals. Those were revolutionary, weren't they? Materials with order, but no simple repeating pattern.
Precisely. And some pioneering theoretical work around that time, by Komodo and others in '87, showed something extraordinary. Even simple one-dimensional structures following a Fibonacci sequence, where each number is the sum of the two before it.
1, 1, 2, 3, 5.
Yeah, that sequence.
That's the one.
Mm-hmm.
They showed it produced what they called fractal energy spectra for electrons.
Fractal energy spectra. So the pattern itself was dictating the energy landscape for electrons in a really complex way.
Exactly. It meant the allowed energies weren't these simple continuous bands like in normal crystals. Instead, they were fragmented, like repeating patterns at different scales, self-similar.
Wow. So not just a mathematical curiosity, it actually changed electron behavior. Fundamentally, it suggested you could sort of sculpt the energy levels in a material with incredible precision. And around the same time, Merlin and his group actually managed to create the first quasi-periodic superlattice.
He's got one.
Yeah, alternating layers of materials but stacked in that Fibonacci order, and they observed similar spectral gaps. The theory was being backed up.
Okay, so the abstract idea quickly got some real-world legs.
Pretty much. And then the crucial insight extended to magnetic excitations, to spin waves. By the early 90s, maybe 93, Liu and Wei did some of the first calculations for spin waves in these Fibonacci magnetic superlattices.
And what did they find?
They predicted multiple magnon band gaps, forbidden frequency zones where spin waves just can't propagate, and a fractal-like structure for the allowed modes, the allowed frequencies.
So the core idea was born. Break that standard repeating symmetry using these, well, sacred geometry.
And you could get incredibly rich, complex spin wave behavior, completely new ways to control magnetism.
That definitely laid the theoretical groundwork, showed what could be possible. But I imagine theories are one thing. Actually making these incredibly precise patterns, especially at the nanoscale, must have been a whole different challenge, right?
Oh, absolutely. A huge challenge. And that's where the story gets really interesting, moving into the experimental side.
Right.
By the 2000s, our ability to pattern materials at tiny scales just exploded. We're talking nanometers here.
Smaller than viruses.
Exactly. And this allowed scientists to finally create artificial magnetic lattices with these complex geometries. For instance, around 2013, Fott and colleagues, they made a 2D artificial quasicrystal. using permalloy dots, that's a common magnetic alloy arranged in a Penrose-like pattern with that five-fold symmetry you don't see in normal crystals.
A Penrose tiling made of tiny magnets.
Pretty much. Now, their initial focus was more on the static magnetic properties, how the magnets settled, but it was a massive step. It proved we could fabricate these complex magnetic patterns. That paved the way for studying the dynamics, the spin waves.
And then came the fractals, which are, even more mind-bending. Patterns repeating within patterns infinitely.
Absolutely. And a really landmark study came out in 2015. Swoboda and his team, they fabricated tiny magnetic films, permalloy again, patterned as Sierpieski carpet fractals.
Those intricate square patterns with the holes repeating.
That's them. And they didn't just make them, they directly measured their spin wave spectra.
What did they see?
They found distinct quantized modes, specific allowed frequencies, and these frequencies were directly related to the fractal's iteration level, how many times the pattern repeated within itself.
So direct experimental proof that the fractal geometry itself was imposing this self-similar structure onto the spin waves.
Exactly. It was clear validation.
So the geometry, the very shape of the structure was acting like a magnetic tuning fork, but based on a fractal, controlling the allowed notes, the frequencies.
Precisely. A powerful demonstration of direct geometric control. It showed the underlying math was dictating how magnetic energy could vibrate. And simulations by Richery and others in 2017, they looked at 1D Fibonacci magnonic crystals.
So back to the Fibonacci sequence, but in stripes.
Yeah, alternating cobalt and permalloy nanostripes in that sequence. They reported a fractal magnon spectrum, too, a hierarchy of band gaps. They even called it a magnonic Cantor set.
Like the mathematical fractal.
Exactly. And they even quantified its self-similarity with something called a Hausdorff dimension. It was about 0.96.
Okay, so these early experiments and simulations really nailed it down. We could build these things. We could see these complex spin wave effects. Theory became reality.
Moved them from abstract ideas to, tangible things you could measure in the lab.
Okay, so fast forward a bit. Moving into the late 2010s and, basically today.
Yeah.
What kind of truly groundbreaking demonstrations have we seen? Stuff that shows the real power and potential of these designs in magnonics. How are scientists unleashing new powers from these patterns?
Yeah, this is where it gets really exciting. One of the biggest developments is being able to directly visualize and even reprogram these systems.
See the spin waves moving.
Exactly. In 2019, Lisiecki and his team used time-resolved X-ray microscopy, a really powerful technique, and they got the first direct, real-space images of spin waves propagating through a Fibonacci magnonic quasicrystal,
Right.
one-dimensional array of nanowires.
What did that let them see?
Well, they saw the crucial features predicted by theory. Multiple magnon bands, these mini gaps caused by the quasiperiodicity. They even saw evanescent spin waves.
Evanescent, meaning they decay quickly.
Right, essentially trapped within a band gap. Some frequencies let waves propagate right through, others excited these localized standing waves. It confirmed the theory, but also showed these quasicrystals offer possibilities far beyond standard periodic ones.
Okay, seeing is believing. But you mentioned reprogrammability. That sounds like a game changer.
It really is. In a companion paper, they showed exactly that, reprogrammability. They designed nanowire arrays where segments had magnetization that could be tuned, adjusted by an external magnetic field.
Okay.
So by tweaking the field, they could selectively activate or suppress certain magnon bands, turn them on or off, basically.
Wow. So you're effectively toggling the band structure of this periodic lattice just by adjusting its magnetic pattern.
Exactly. It shows the potential for scalable magnonic quasicrystals where you can dynamically adjust the response, almost like a magnonic logic circuit you can rewire on the fly.
Reprogramming a spin wave circuit just with magnets?
Mm-hmm.
That genuinely sounds like a whole new level of control. How big a deal is that shift from static design to dynamic function?
It's transformative, really. We're moving from building devices with fixed properties, set in stone when you make them,
Right.
to devices that can adapt, change their behavior as needed. And the innovation doesn't stop there. Another team, Watanabe et al. In 2020, they created a 2D Penrose tiling antidot lattice.
Antidot. So holes in a magnetic film.
Exactly. A permalloy film with a Penrose pattern of nanoscale holes punched into it. And they found something really cool.
What was that?
Spin waves didn't just spread out, they propagated along specific worm-like nanochannels that are just inherent to the Penrose structure itself, these Conway worms.
Conway worms. So the pattern itself creates pathways.
Yeah, acting like built-in one-dimensional waveguides.
That's incredible.
And get this, A single input microwave signal actually split into two distinct magnon beams. They traveled through different quasi-1D channels. It performed an automatic demultiplexing of the signal.
Wait, so the geometry itself acted as a signal splitter, sending parts of the signal down different paths without any extra components.
Precisely. One input, multiple separate outputs, all operating at the same frequency but in different spatial lanes. It's a totally novel multiplexing function that seems unique to these quasicrystals.
It's like the material's smart enough to sort signals on its own.
In a way, yes. It showcases how these aperiodic 2D magnonic lattices can naturally create multi-channel circuits. Could really simplify things for magnon-based signal networks. And, just quickly, further simulations on CRPSQ fractal anidots in 2021.
The fractal holes again.
Right. They showed each fractal iteration, each step of making the pattern more detailed, splits the allowed magnon modes in a predictable recursive way. It perfectly mirrors the fractal's own geometric recursion.
So a one-to-one link between the geometry's recursion and the spin wave's recursion.
An elegant, almost beautiful connection between the pattern and the physics.
Okay, this clearly means these intricate geometries, these sacred patterns, are way beyond just abstract curiosities now. What does all this mean for, real-world applications? What's the bigger picture here for us, the listeners?
Yeah, connecting it to the bigger picture, it means we can potentially design materials that inherently perform complex functions just because of their shape.
Like what?
Well, think about multiband RF filters for, say, next-gen wireless communication, 6G and beyond. A single device, geometrically designed, could maybe filter many different frequencies simultaneously, making our phones, our networks, much more efficient.
Okay, that's practical.
Or novel signal processors that automatically demultiplex signals like we just talked about with the Penrose tiling. But the ultimate vision is maybe even more profound.
Go on.
Using these fractal and quasi-periodic networks as the basis for neuromorphic computing.
Neuromorphic. Brain-inspired computing with spin waves. That's a huge leap.
It is. But imagine creating chips inspired by the brain where spin waves mimic neural activity, processing information in a totally different way, potentially much more energy efficiently than current silicon chips.
That could revolutionize AI, data processing.
Absolutely. And we're even seeing hints of other weird, useful effects, like magnons with hierarchical structure and something called non-reciprocal propagation found in actual bulk quasicrystal materials.
Non-reciprocal, meaning they travel one way but not the other?
Exactly. Like a one-way street for spin waves. And crucially, this can happen without needing a big external magnetic field, which is usually required. That hints at building integrated magnonic circuits with built-in diodes, essentially, preventing signal reflections, boosting efficiency.
So these phenomena aren't just lab tricks anymore.
No, they manifest vividly in magnon dynamics. It's really opening up entirely new regimes for wave physics and for device engineering, a genuinely new frontier.
It really is a fascinating frontier. Okay, so to kind of recap this captivating deep dive.
Right. We've journeyed from these abstract mathematical patterns, Fibonacci, Penrose fractals, to seeing them physically built into magnetic materials.
Tangible manifestation.
Yeah. And we've seen how these complex geometries can precisely control how spin waves behave, enabling things like fractal band structures, inherent signal splitting, even dynamic reprogrammability.
It's just a powerful reminder, isn't it, that sometimes the most elegant solutions in science, the most powerful ideas, are found by looking at the fundamental patterns of the universe itself, these sacred geometries.
It really makes you wonder.
What other hidden mathematical symmetries are out there in nature, just waiting to be uncovered? And how might they fundamentally transform our future technologies? Maybe they hold the key to completely new ways of computing or sensing or communicating that we can barely even imagine today.
It's an exciting thought.
Absolutely. Well, thank you for joining us for this deep dive into the really surprising connection between intricate geometry and the tiny magnetic waves that could maybe power our future.
Hope you enjoyed exploring these ideas with us.
We love bringing you these surprising nuggets of knowledge. So if this deep dive sparked your curiosity, please consider suggesting new topics down in the comments. We're always looking for what you want to unpack next.
Yeah, let us know.
Until our next deep dive, stay curious.